So now all we're left with is developing the loop body itself, the command S in the loop body. And let's have a loop at that. So the part that we're now going to look at is highlighted in yellow. And we once again return to our example where we add the contents of vector x to those of vector y. And this is again the loop invariant that says that the first k elements have been left alone so far and the rest of the vector has already been updated. And in blue we highlight what we are going to look at next. And remember that we have to somehow force progress, and notice that this particular loop invariant inherently has the property that we are going to go from the last element in the arrays to the first element in the arrays. So therefore we want to pick an update to the loop index where k is being decremented every time through the loop, and that obviously forces us to finish, because we saw that the loop guard in this particular case is that 0 is less than k, and it's easy to see that then the bound function is just k itself. So here we're focusing on just what is in the loop body itself, and we've given ourselves some room to maneuver. Now notice that we know that we have to end up in a state where the loop invariant is true at the bottom, and we've chosen to update our loop index k by decrementing it. So from that we can compute what the weakest precondition is. That's a matter of substituting in k minus 1 for every occurrence of k in the loop invariant. And then we notice that we are marching through the matrix backwards, and therefore it is the first element in the range of the second quantifier that was last added. So what that guides us towards is peeling that one off, splitting the range to explicitly expose the elements of y and x indexed by k minus 1. Then we can do the same thing for the precondition for the loop body, and there we peel off the last element of the first quantifier, because that's the element that actually is going to be updated this time through the loop. So if we then get rid of some of the clutter, we can compare and contrast, and we can notice that indeed it is the element indexed with k minus 1 that changes from before the command s sub u to after, and that lets us realize that it's yk minus 1 that is going to have to be updated, so we assign some expression to that. Then we compute the weakest precondition of that, and we get this right here. Every occurrence of yk minus 1 is now replaced by that expression. And then we can read off that the expression should just equal y hat of k minus 1 plus x of k minus 1. And then we go to what was exposed in the precondition for the loop body and recognize that y hat k minus 1 is actually equal to what is stored in yk minus 1. And therefore that is what we actually plug in. And that leaves us then with the update yk minus 1 is updated with yk minus 1 plus xk minus 1, which is obviously a little bit ugly. Wouldn't it have been nicer if this was yk becomes yk plus xk? But it also demonstrates that it would be easy to make an indexing error here and indeed assign yk plus xk to yk, and then you would have gotten the wrong answer. So then you plug that all into the worksheet for deriving the loop, and now we have completed our derivation of this loop. Now alternatively, we could have chosen to decrement k before the update s sub u, and then actually if you work through it, the update to y would have been yk becomes yk plus xk, which is a little bit more pleasing to the eye. But either way we end up with a correct loop. So in summary, given a precondition and a postcondition, we can derive loop invariants. If we then pick a loop invariant, then that loop invariant together with the postcondition allows us to derive the loop guard. Given the precondition and the loop invariant, we can derive the initialization command. Given the loop invariant and an update to the loop index, we can derive the loop body. So we have to have some means of forcing progress towards completion. All of these steps are prescribed by the precondition and the postcondition. Read through it again. Given a precondition and a postcondition, we can derive the loop invariance. And then once we pick a loop invariant, all other parts of the loop are actually prescribed. The program and its proof of correctness are developed hand in hand. In the end, we not only have a correct loop, but we also have its proof of correctness. And we would think that perhaps this would have made Dijkstra happy.